let's go ahead and continue with electrolysis. Most of you got the molten equations happening at the electrodes. You did not have to state which was happening at which one, but I went ahead and did. And I said that at the anode, I had the I minus becoming 1/2 I2 plus E minus. If you doubled that, that was fine. You could do that. And the other one is at the cathode, I had Ca plus 2 plus 2E minus goes to calcium. You do not have to get the states of matter if they are not requested. In the next one, they ask for the same thing. They tell you this is redox. Identify what's oxidized and what's reduced and explain the oxidation number. So here you should have said that I minus is oxidized as its oxidation number increases. And you should point out that it's from -1 to 0. And then calcium plus 2 is reduced as its oxidation number decreases. And that's what reduction is, from +2 to 0. Okay, so that was our first bell work. That's actually considered to be not that part of a level of bell work. And I saw almost all of you got it correct. The only one that required the extra thinking was this one. And actually, this is in your homework. So this is actually the first part of a question that's in your homework. I know because I solved your homework yesterday, and then I went through and did the lesson, and I was like, oh, so freebie homework question, which means y'all might have got it wrong in the homework if I didn't show it to you now. Half equation that occurs at the anode is given. They tell you that you're electrolyzing KiAQ. So what happens at the cathode? At the cathode, you have a choice. It's aqueous. That means you are either reducing K plus or H plus. You're supposed to look at the activity series, which you are supposed to actually have memorized, at least in a basic manner. Am I going to produce a group 1 metal in water, or am I going to produce H2 gas? That's the question. You're either going to produce K solid, and it would have been K solid. If you made it, you would have made it in its standard state. Or you're going to make H2 gas. Which one happens? You make H2 gas. You don't make K solid because it would explode in water. That's not what happens. It is more active than the H plus. The H plus is what gets reduced here. Yes.
How do we know the state of matter? I mean, iodine without us.
It's typically the standard state of matter, so I wouldn't trust that. That's why they gave you that information. But you should know the standard states of matter. Yes.
Wait, why didn't we do what's it called? H plus for the first question?
That is a interesting question that you ask and brings up an idea. This is aqueous. Aqueous means that what I have is in water. This is molten. No water. This is liquid CaI2. Like when I had to make the potassium chlorate molten for the gummy bear experiment to turn it into a liquid, when I made it molten, I did not add water to it. Molten means I'm literally adding enough energy to change it from the solid phase to the liquid phase. Molten and aqueous are two different conditions and have to be analyzed differently. Does that make sense? Yes, we're good with that? So that's why here we consider water. Here we didn't consider water at all. Didn't matter because there is no water here. That's the big difference. And that's why I thought people might get tripped up here. All right. And this does include state symbols, so we weren't done. I was just addressing the question. So what are my state symbols here? H plus would be aqueous, and H2 would be gas. And I should not put a state symbol for an electron. Please don't do that.
You sure?
We'll go over the tests on Wednesday. For those of you who are here on Wednesday, I'll be giving you back your quarterlies.
Yeah.
We have 3 hours that day. Just so you're aware, if you didn't already know, Tuesday and Wednesday you will be holding in your first class if you are not PSAT testing. Tomorrow you will be in your second period for 3 hours. And Wednesday, you'll be in your first period for 3 hours. So I will be putting a bunch of review activities and doing a titration lab. I will fill your time. It will not be you. We will get our practice that day. Practice and review. All right, so objectives. Notice there are only 2. They are both math objectives. And the funny thing is, if you read the formulas out, I mentioned this last class, it's hilarious. I kind of wish this lesson was on Halloween, but it's not. I was one day off from, sometimes I do this lesson on Halloween. So the first one says, state and apply the relationship flee. That's what the letters spell. Flee. Which relates the Faraday constant, which we're going to learn today, the Avogadro constant, that's something we should be aware of, and charge on an electron. Those 3 are related to each other in this specific way, and we'll be learning about that today.
Yeah, because Avogadro is L.
Yes, Avogadro's number is L now. And it always has been if you look at the back of your periodic table. Look at the letters in the back of your periodic table. What did they define Avogadro's constant as this whole time?
There's no
L.
N in Avogadro.
It's L and then loser.
Don't ask me.
There's no N in mole.
Exactly. Exactly. Ask the committee who made that. They're probably not alive. But anyways, calculate. It's been a while. Calculate the quantity of charge passed during an electrolysis using the quit formula. So you've got the flee formula and you've got the quit formula today.
Guys, we have to quit and
Quit, flee. It's just like telling you all the signs. Yes.
It also only has only 2 objectives, which is like
Terrifying.
more worrying than both of those.
Okay. So
Well, the second
Q
one is A&P.
is actually in physics what we call charge. It's represented by the letter Q. And then I is the amount of current. So Q is charge, the total amount of charge. I is current. And then T is time. So we'll be learning, this is actually a physics formula. So sometimes we get a little bit close into physics ideas. So for those of you that are going to take physics, this will be in a physics class. Some topics in chemistry are in physics. Another one is chemistry. Thermochemistry is definitely in physics. It's called thermodynamics. All right, and then the mass and volume of a substance liberated during electrolysis. So we're going to be doing a bunch of calculations today. You ready? All right, so beforehand, I basically copied the notes and then just added a couple to them. So these are pretty much the notes from last class that I did to finish, and then I added a couple of additional slides. So we were at this topic still of electrolysis and how to predict the equations, and that's why the bell work was all about that. Those first bell work questions were actually questions that would have been in last class's lessons, so some of you had solved them ahead and knew what the answers were, except for the last one. So electroplating is the process of taking and depositing a metal through electrolysis. When you have a low activity metal like copper and you apply electricity to it, you can get copper in its standard state, which is copper solid, and then it'll just plate on whatever your cathode is. So electroplating would happen at the cathode. So this happens at the cathode. And this is a way that, for example, this is how they make pans that have different linings for cooking. They use this process of electroplating the metal that you want on the top. And that was just the end of what we were doing there. So we are jumping straight into the math. You all ready? Yes.
Does that only happen with copper and silver and gold?
It happens with low activity metals. It's aqueous. Happens with low activity metals. All right, so determine the mass produced of an electrode in an electrode during electrolysis. So you can produce the mass that's being electroplated with this method, or whatever you're producing, you can determine through this method. So this is the quantitative analysis part. This is called the quit formula. I remember it as something else because I'm a chemist and I like changing letters. I don't like the physics letters. So I remember it myself as the CAP formula, or you could remember it as the CAP formula. Whichever one works for you.
I'm couch, so.
I like this formula. Why? Do I like it this way? Because this tells me the units I'm plugging in. So instead of, Q, I, and T, I use this is coulombs. So however many coulombs I have, that's the charge unit. Unit of charge is coulomb. And A is amperes. So if you've ever heard of amps, have you ever heard of amps? Where have you heard of it? Guitar.
Talking about cars.
What's a coulomb?
What?
What's a coulomb?
Coulomb.
Oh, coulomb.
Coulomb. Right there.
Charge.
The charge pair. It's basically just the amount of charge, quantity of charge, how much charge is there. More coulombs, more charge. And Q is the physics letter for charge. I like C for charge. It makes more sense in my brain. That's why I said I'm a chemist and I redo things myself to what I remember. So when I was doing the homework, I solved it always using this formula, but you could use the quick formula if you prefer. That would be how it would be presented in a physics class. And so
Wait.
current is an amp, and then T time is in seconds. That is our standard unit of time. They will often give you questions, minutes or days, and you have to change it to seconds. Yes, Luke.
So, alright, so I have a question about like electrolysis.
Yeah.
So like AG CL is like barely soluble. So if we were to do electrolysis with that,
That would be very difficult because it would not have much coming out of it, so you would barely plate any silver. So what you would likely see is wherever your electrode is, like just a scattering of a tiny amount of silver instead of getting an actual good result.
but it wouldn't more of the silver dissolve in the water, which then would cause it
Dang.
to what?
Maybe over a very long period of time, you'll get what you want, but then how much energy are you using with the battery to make that happen? So,
UIT.
yeah, it can happen. It's just,
Wait, you
it's
need
not
to-
ideal.
today?
You'd rather use something like silver nitrate, which is soluble in water and will readily plate. All right, so the mass of the substance that's being electroplated is going to depend on two things. How much time passes? The more time, the more you're going to get. As long as you still have enough of your solution that still has that metal in it. And the strength of the current. The stronger the current, meaning the greater the voltage, right, that's being applied, the faster you're going to get your electroplating to happen. And so this is the formula that gives us what we need. And so we're going to go ahead and see how do we apply it very shortly. The next thing, though, is you need to know this new constant called a Faraday. So the Faraday, which by the way is on the back of your periodic table, you will be using this a lot for this unit. The constants on the back. Faraday is the amount of coulombs that you get, so the amount of charge in 1 mole of electron. So for every 1 mole of electrons that passes, how much charge is it that you have? And so that's called a Faraday. And so if I had this equation, let's say I had 2 moles of electrons, how many Faradays, or not how, well, you could say how many Faradays would I have? If I have 2 moles of electrons, I have 2 Faradays. And then how much charge would that be? If I had 2 moles of electrons.
Like,
So it would just be double, right? So 2 moles of electrons would be 2 Faradays, which would be 2 times 96,500 coulombs for the amount of charge that's passed through. And so we're going to be using this the same way that we use any other relationship. We're going to do dimensional analysis, or some of you think of it as stoichiometry to solve these questions. Yes.
Wouldn't the charge change depending on the atoms we're using?
It's a redox process. It's just however many electrons you have, that's how much charge you have, because each electron has its own charge. And you'll see that on the back of your paper here, the electronic charge, that E right there, that's the charge of a single electron. So that's negative 1.60 times 10 to the negative 19 coulombs. If you multiply that by Avogadro's number, you get 96,500 or something very close to it. And so that's actually one of the equations we'll be looking at in just a little bit. But let's take a look at how we would solve an electroplating question. So it says calculate the mass of silver deposited at the cathode during electrolysis when a current of 1.8 amps flows through an aqueous solution of silver nitrate for 45 minutes. And so if I want the mass of silver, the first thing I'm going to need to get is the charge. I have to know how much charge is in carry. So the first step, so right, step one, is we need to find the charge, which you can remember it as the quick formula, or using the units, it's like this, E equals A times S. That's the way that I like to use it. So I need the charge. Charge for me is the letter C because that's the amount of coulombs. And so what do I need to have to find the charge? I need the amps and I need the, what is S? Seconds. So 1.8 amps, got that. And then how many seconds? I've got 45 minutes. Can you change that to seconds?
2,000 circle free.
I would do 45 times 60. And so that would give me my amount of coulombs. And that's my first step. So that's going to be, I hope I did this last week. I thought we could get this far last week. We did not. I got 4,860. Let me know if you get something different. 4,860.
I got 486,000.
What did I get that?
Oh, it's 1.8. I thought it was 180.
1.8 times 45 times 60. 4860. I just tried to get it. I got that same thing. So this is the amount of charge that's passed. So we can directly relate the amount of charge that's passed to the amount of moles of what? Electrons. And that's what we call the Faraday. And so we're going to need to go from the charge to the moles of electrons, but that's not what we're being asked for. What are we being asked for?
So
So how could we possibly get from moles of electrons to mass of silver? You're going to need the equation. The equation at the cathode. So what would the equation at the cathode be for silver nitrate? Ag plus what? 1E minus goes to A solid, which you're electroplating, right? You need that equation. And you're going to need that equation for other questions because the ratios are not always 1-to-1. In this question, it is 1-to-1, so the math will be easy. If you made a mistake and didn't include this, you might come up with the right answer. But for future questions, you're absolutely going to need your balanced equation for whatever it is they're asking about. Here it's silver, so this is the equation for the electrolysis for silver. Okay, so then I'm going to go from moles of electrons to moles of silver using something called stoichiometry. And then I'm going to go from moles of silver to grams of silver, because we can do that. It's something we should be comfortable with. So then, where do we begin? 4860. Put it over 1. How do I go between coulombs and moles of electrons? What's the number? It's on this paper. It's the 96,500, or you can use it as it's presented to you on this paper in scientific notation, which is 9.65 times 10 to the 4th. I usually just like writing out the whole number. So I'm going to write 96,500 coulombs to cancel. And what goes on the top?
1 more.
1 mole of electrons. That's how we get from charge to an amount. So this is the amount of moles of electrons. Now, how do I get to silver? In this electrolysis that's occurring, every mole of silver gains 1 mole of electrons. So it's a 1-to-1 ratio. So it's just, if you want to write it out, just to make sure you got it. Some people just do 1/1. But the reason I label is just to make sure we don't make a mistake. So 1 mole of electrons is 1 mole of silver, right? And what else? Now I'm in moles of silver. But where do I need to be? Grams. How do I get to grams? multiply by the molar mass. So the molar mass of silver is 107.9. And then this will get you your answer. I get 5.43 grams of silver. See if you get the same. You could stop at moles and then just use the moles formula to multiply by molar mass, but you've got to multiply by molar mass in the end.
That's the final answer.
What?
Is that the final answer?
That's the final answer. That's the textbook question. So it's almost as easy as it can be. So the first step would be finding the charge, and then the second step would be finding the mass. So you have to find the charge first separately as its own formula, and then you use dimensional analysis to go from the charge to whatever it is you're looking for. Here you're looking for the mass, but you could be asked for other things, which we'll see shortly. And it says in the standard you could be asked for mass, you could be asked for volume. We'll be using the volume of a gas formula again. Ready to continue to the second example? All right, second example. A student passes a constant electric current of 0.15 amps through silver nitrate again. Using pure silver electrodes for 45 minutes, the mass of the anode decreases by 0.45 grams. Would you use this data to calculate the charge on a mole of electrons? So what would we do here? So it's asking us to find charge on a mole. So we want the amount of charge, right, for a mole. So we need the amount of charge and we need the amount of moles to be able to divide those two numbers to get the amount of charge per mole. So they're asking us, come up with the Faraday yourself using this experimental data. That's what they're saying. Come up with the Faraday yourself, prove it. So if you just wrote the Faraday here, you're like, oh, look at the back of my paper, it's 96,500. You would get no marks because they're asking you to use this data to figure out what the Faraday is. And so what of this data could we use to find the charge? The amps and the time, right? So we can find C by using, I like to call it this, but you can call it the quick formula if you want. I like putting it in the units. So then find C, I've got my amps are 0.15. My seconds are 45 times 60. Are you okay with that? It's 45 minutes times 60 seconds in a minute. And I get from that 405 coulombs. So that would be my top number. How would I get the bottom number? So find moles of electrons. How could I find the moles of electrons? What have they given me that can give me this information? I have the grams, so I would just work my way to moles of electrons. It's the same equation as last time, isn't it? Because it's still silver nitrate and they're still talking about silver. So it's still this. So find moles of electrons. So we've got 0.45 grams. So what should I do with that first? Change that to moles. How do I change grams to moles? Grams of silver. What do we do? Molar mass. So what do I do with the molar mass? Divide it by the molar mass. You can either use the formula or use dimensional analysis, but you've got to divide 0.45 grams of silver by the molar mass. So the molar mass of silver is 107.9. And that's the grams in a mole. If I go this way and I just use the mole formula to do grams divided by molar mass, then I'll get 0.00417 moles of silver. Would you agree with me that that's also the amount of moles of electrons? I always feel like doing the math thing here. You know, do you know what math thing I'm talking about? This. Some of you will know this.
Therefore.
Therefore, you would have 0.00417 moles of electrons. If you don't know what this is something you would see in any higher level math class. It's therefore. So 0.00417 moles of electrons. And then that would be the bottom there. And then you would have 405 divided by 0.00417. And what do we get? I get 97,100 to 3 significant figures. Coulomb per mole. Notice that's not exactly the same as what you have on the back, right? Because it was determined experimentally. And then I thought to myself, I was like, I could ask you a follow-up question. What is the student's percent error?
No.
Yes. What is the student's percent error? We can figure that out. Whoever the person is that did this, what is their percent error from the established formula? How do we figure that out? Something you have to know for paper 5, right? So how would we figure that out? What's the formula for percent error?
There's something that's
It's the error divided by the established accurate true value, whatever the accepted value is. You all might remember I taught this, I think it's the first lesson in pre-A. So it was literally unit 1, lesson 1 or 2. It was one of those very beginning of pre-A. We did this formula. So how would we calculate that here? The error would be what? It would be the difference between 97,100 and what it's supposed to be, which is 96,500, right? Over what it's supposed to be, which is 96,500 times 100%. So I get a 0.6% error. Check to see if you get the same. In the grand scheme of things, does that look like it's very far off now? It's less than a 1% error. So some of you will look at that and be like, 97,000 is supposed to be 96,000. But
Oh, never mind.
did you multiply by 100 in the end?
Multiplied by 10 on the third.
Okay. All right, so
Question, what happens if it could be more A minuses? Like, let's say you have an element that has 2 E minuses need to add.
we have practice questions for that. Yes.
Why is the mass of the anode decreased by 0.45?
Because it's the anode. The mass will always decrease at the anode and increase at the cathode. Because the anode is actually like taking some out from the actual like what the anode's made out of. If it's a reactive metal like silver, well, reactive enough for it to take it away, and then it goes to the cathode instead. All right, so there's a couple of electrolysis half equations that you have to know for the Cambridge exam. But if you paid attention to how I taught you how to do this last class, which we all failed on the bell work, but that's okay. Then you are actually supposed to be able to come up with this off the top of your head. Meaning that if you have the electrolysis of sulfuric acid, that's H2SO4. Your cation here is H+. Your anion here is SO4 - 2, but it's aqueous. So in H+, we know that H+ is going to be reduced, right? So what does H+ get reduced to? H2, right? And this is the equation for that. You have to know the equation for that reaction of the cathode. At the anode, you need to know that if sulfate is in an aqueous solution, it is not sulfate that gets oxidized. What gets oxidized instead? It's not sulfate. It's OH minus. So OH minus in water is what gets oxidized. And so it would actually be OH minus that gets turned into O2. That's what we had went over last class. And then you would have to do the proper balancing for that, which would give you this. So that's why I said if you paid attention to what we did last class, you'll be able to create these equations as we go along. And if you don't get what we did last class, then I'm going to tell you to memorize these equations by heart. The H+ and the OH minus one and when to use them. But we'll keep creating them from scratch so you can practice how to do it. And then sodium sulfate is the same thing. Sodium itself, if it's aqueous, is not going to get electrolyzed. It's going to be H+ that gets reduced. And the same thing with sulfate again, it's going to be OH minus that gets oxidized. Why does this matter? Well, someone asked Philippe and Como. Well, what happens if there's multiple electrons? We're about to address that in the next few examples. Oh, and by the way, this is a example. I just have a little diagram here. We are going to do a lab in a couple of weeks. When I have the materials, I'll have it on the schedule as soon as I'm ready. We are going to do electrolysis, and we're going to do a galvanic cell in a couple of weeks as a lab. First lab is this week. It's a titration, and then we'll do the other one before we take the test. All right, so let's try this one. Check up 6. That means we're still in the textbook. We're not to the Cambridge questions yet. Calculate the volume of hydrogen gas produced at RTP, room temperature and pressure, when a concentrated aqueous solution of sulfuric acid is electrolyzed for 15 minutes using a current of 1.4 amperes. So before we even begin, do you think it would be wise to figure out the equation for the electrolysis? Because you're going to need to use it for the math. Maybe first we want to find the equation that we need. What equation do we need here? What are they asking me for? Hydrogen. So what do you think is the equation that we need? We're electrolyzing sulfuric acid. Do we need the one for hydrogen or the one for the OH minus? Do we need H plus go to H2 or do we need OH minus go to O2? Which one do you think we need for what we're being asked for here? This, right? So then what would that equation be? H plus goes to H2. Yes. Fill it in. It doesn't matter how you balance it as long as it's accurate in the end. Meaning you could do the way that you see it here, but you don't have to. What's another equivalent way of writing this? That I think I saw some of you write in the bell work. What would we do? What do we need to balance here still? What's not here? That's the electron. Does the electron go on the left side or the right side? The left side. That's why we spent that first lesson going over that, right? Now what? You can. I heard both correct answers. You can either multiply by 2 or do 1 over 2. Which one would you all prefer? Multiply by 2? Okay. So then multiply by 2. But if I multiply my H plus by 2, I now have to multiply my electrons by 2 as well, right? So you could have said this or you could have said this. The ratio is the exact same, regardless. It is up to you. You make a choice how you're going to balance it. You would get the right answer regardless. Okay, so we've got our equation. What's the next thing we should do? We have an amount of time, we've got a current, and we're looking for how much hydrogen. What should we find first? Step 1 is find C, right? Find the charge, which in physics they call that Q. Q is the unit for charge. So I'm going to go ahead and find my coulombs, which I need my amperes times my seconds. My amps are 1.4, and my seconds are 15 times 60. Are we good with that? So then I get from this 1,260 coulombs.
Mhm.
That's how much charge has been carried by however many electrons we've used. So then now we've got to find what? That was step 1. What's step 2? Step 2 is we got to find the volume of hydrogen gas, right? But that's going to be something that requires multi-steps itself because we have got to go from coulombs to, Lisa was saying, moles of electrons. So we make a pathway. That's what I did all the way back in pre-ACE chemistry. I was like, if you don't have it in your head, you can write out a pathway and then you know what to follow. So coulombs goes to moles of electrons, then moles of electrons would go to what? Moles of hydrogen gas. And then we want volume. So we must have a relationship between moles of hydrogen gas and volume, right? Of H2. So we're going to need these steps with this as our starting amount, right? So 1,260. coulombs over 1. What is the number for coulombs to moles? And that's something that I have memorized, but you have it on your paper. What is the number for coulombs to mole? That's what we call the Faraday. So it's 96,500 coulombs in 1 mole of electrons. Now, how do I go from moles of electrons to moles of H2? You all said you wanted to use this equation, so I'll use this one, but you could use either. I want to cancel out moles of electrons, so what number do I need to put on the bottom? 2. 2 moles of electrons is for 1 mole of H2. That's how we use the 2. And then, I'm not done. What do I need to change hydrogen to? Out of moles and into what? Volume.
24.
What's the right number to use? There's 2 of them. Are we in STP or room conditions? Room conditions. So the right number to use is 24. So 1 mole H2. And where do I find the 24? Where do I find that number? It's also on this paper. The 24 and the 22.4. And so that's the M cubes. And they had these. How very nice. So then from here, I get double check my work, but I got 0.156 DM cubes. Check to see if you get something different.
Oh.
They did not tell me what unit to put my volume in, so I can leave it at DM cubes.
What if they 157?
0.157 is right. I'm checking my significant figures now. You're right. 0.157.
It could be 1.1, it could be 0.156.
So we have one that's your turn before we get to Cambridge questions. All right, next slide is your turn. I'll give you 5 minutes. Calculate the volume of oxygen at RTP. And I'll check your answer when you're ready in the next 5 minutes. Let me know because I have something for you if you get it right. Something fun. Like you cook, you said? All right, so try this question. You good? Strategy? What happened? It's saying the same thing. You just have to recognize it's for oxygen, not hydrogen. You have your final answer?
I don't know if it
You can write your answer either in BMQ or CMQ, but I don't think I have that.
Oh.
Did you consider foods that's I don't see that in your work? Okay. In commemoration, I have a little
Big green.
I've got gummy bears to give away.
This week,
Yeah.
not being locked in on Stefan, who's sending me real strength last time.
Who?
Stefan.
Seven. How y'all doing over there? You finished everything? Oh, you said you was real from the book. Yeah. Mhm. All right, you've got 3 minutes. Show me your answer if you have it correct. I do have some gummy bears to sacrifice to your stomach. Yeah. Yeah, they got it. Yep. That is not it? Hmm.
I'm not done.
Not done? You said let him cook.
Yeah, I'm cooking. Just let me cook.
Yours is off. Check them against each other. It might be a math thing. Like you might have entered something in the calculator wrong. All right, raise your hand when you're ready for me to check. This number.
Yes.
No.
I think this was wrong. It doesn't look right to me.
Yeah, it's not this relationship. There's something off there. Let me check yours, Kaylee. Something off. Think you're off? Oh. I'm done. All right, one more minute till I go over the answer. Something off. That's not the final answer. Yes. Styrofoam cup? What do you mean? For what?
Oh, I can't remember. It's because it's.
Here.
That was okay.
All right, raise your hand if you're ready for me to check. Found it there.
I got that one.
You did not. You did it, right?
Of course it has to. Yeah, that's not 40. Bro.
Checking. Yes. Did we get it? Yes. We get it?
Okay, I'm not.
All right.
I have Christmas
No.
colors.
Taking it back. Coming for not today. No.
Oh, yeah, it does have at 40. Man, why are you giving us about 40?
I love her.
Okay, so let's go ahead and go over the answers. Some gummy bears, some additional gummy bears are getting sacrificed. It's too late. Okay, so let's take a look and see where you might have made some mistakes. The first thing is, what's the proper equation for oxygen? This is the one that's OH minus going to O2, right? So you've got to have that equation down. So how would we make that? OH minus goes to O2. How would we make that? Yeah, one H2O is correct. That gives you hydrogen. Now what? Put a 2 here. Now what am I still missing? What am I missing right now? My oxygens still aren't correct. I've got 2 on this side and 3 on this side. So what would I do? Make this 1/2, which some of you did. And then electrons. Which side do the electrons go to and how many? Product side and 2. This is going to give us our ratio we need for later on. So then we do our find the charge first. So that's C equals A times S. Amperes this time are 0.7. Seconds is 55 times 60. So this would be, and then you got here, 2310. So I got 2,310 coulombs. And then from here, I want to get from coulombs to moles of oxygen. So 2310 times 96,500 coulomb 1 mole. And here's where, if we made a mistake, we made it right here. 2 moles of electron is for 0.5 moles O2, or 1/2, however you're going to put that in your calculator. I would put put 0.5 because I like that number better in terms of entering it in my calculator. Moles of O2. And then, as I said, if we made a mistake, we made it right there because it comes from here. The electrons versus the amount of O2. That stoichiometry was the issue. And then 1 mole of O2 is 24 dm cubed. So if you did all of this correct, you ended up with 0.144 dm cubed. All right. We're done with the textbook questions. We are now ready to look at the Cambridge paper 4 questions on this topic. So let's take a look at our first paper 4 question.
There's like way that stuff.
A molten magnesium salt is electrolyzed for 15 minutes. 4.75 times 10 to the 22nd magnesium atoms are produced at the cathode. Calculate the value of the current used. So what would I do this time? Go ahead, Ramon.
Avogadro's number.
Okay, so we're going to want to use Avogadro's number at some point. That's for sure. That's going to get us out of atoms. What else? What am I trying? What am I looking for? What is current? Current is A, right? You're looking for something else in the formula. You're not looking for coulombs this time. You're looking for the amps, which means you need to have the time and you need to have the coulombs, right? But we don't have the coulombs. Do you see that we don't have the coulombs provided to us? So we can't use this formula until we have them. So what should our first step be this time then? Step 1, find coulombs, right? But we're not going to be able to use the formula to find the coulombs. We're going to have to use our amounts of atoms. What else would we need to go from atoms to coulombs? We need Avogadro's number, okay. That's going to get us from atoms to moles of magnesium. How's that going to get us to coulombs?
Oh, we're going to
We need the equation because we need to go from moles of magnesium to moles of electrons. And moles of electrons will get us to coulombs. So what's our equation?
I forgot negative 23 or 23.
Molten magnesium salt. What's the equation? Mg. Mg what? Plus 2 plus 2 electrons goes to Mg. So you have to be able to come up with that equation. And note the relationship because magnesium is a group 2 metal. It has to gain 2 electrons, right? Okay, so 4.75 times 10 to the 22nd Mg atoms over what number? 1 times, now what? What number goes on the bottom? 6.02 times 10 to the 23rd. You know, we had Avogadro's day last Thursday. Atoms in how many moles? 1.
That means we're going to get to use Avogadro's.
Now what? Yeah, we didn't get there in time. It took us too long. Now what? How do I get to moles of electrons? Times 2, right? 1 mole Mg, 2 moles of electrons. Am I done? Does that give me the charge? What do I need to get to charge? 96,500, right? So 1 mole of electron is 96,500 coulombs. So what does that give me for coulombs? If you agree with me on that. I do all this math. Make sure when you plug this in your calculator, you may have forgotten, it's been a long time. If you divide by multiple things, you need to put parentheses around them or on your Casio calculator. I think it's easier if you have the Casio, you just put it all on the bottom. I get 15,228. Let me see Does that make sense? Are we good with that for the amount of coulombs? That's step one, right? That's not the answer. What do we have to do now? So now step two is we've now got our C equals A times S formula, but we're solving for amperes, right? This time we have the coulombs and we have the seconds. We're solving for something else in the formula. So this would be 15,228 equal A times how many seconds? 15 times 60, right? Which is 900. So 15,228 equals A times 900. Divide by 900 on both sides. And our final answer is, I got 16.9. And how many marks is this worth? 6. Where do you think the first mark was? The coulombs. So if you got the coulombs correct, that would be 1 mark. And if you applied this formula with the coulombs, that would be a 2nd mark. If you got the coulombs wrong, but you applied the formula correctly, you would get what? Error, carry, forward. Or 1 out of 2 marks, right? Ready for the next Cambridge question? So that was Cambridge question number 1 on this topic. This heavy, heavy math topic. All the stoichiometry. Continue. All right, let's see what else they could ask of us. An oxide of iron dissolved in an inert solvent, meaning that does not react, is electrolyzed for 2 hours using a current of 0.8. The electrolysis products are pure iron and oxygen gas. The mass of the iron produced is actually 1.11 grams. Calculate the oxidation number of iron. Show all your work. It says show all in bold. How many marks is this worth? 3. So what could we do here? What are the oxidation numbers? What's that another word for? What are they asking us for? The oxidation number, what's that? If it's a metal, it's the charge. They're asking us for the charge. Iron is a transition metal. It can have variable charges. So they're asking us from this experiment, can we figure out what the charge is? So how would we do that? We know the equation would then be Fe with whatever positive charge, right? We don't know. Some people would use the letter X. I like to use question mark. Same thing. Plus question mark electrons, right? Equals Fe solid. That's being plated. Yes, Ramon.
We can find out the moles of Fe.
Right. So Ramon's on a good path. So we can find the moles of Fe. What else do we have the information for that could help us figure this out? Do we have anything that could get us to moles of electrons so we could develop a relationship between the two? Isa? We can find the moles of electrons. We can find the moles of electrons. And if we do the moles of electrons divided by the moles of Fe, wouldn't that be how many electrons are transferred for every mole of Fe? So that's the strategy. Let's find the moles of iron first. So how do we find the moles of iron? That's easy, right? We just take the grams and divide by the molar mass. So 1.11 grams of Fe divided by 50, 5.8 grams per mole. And that gives us how many moles of iron? I get 0.01989. That's what I got when I solved it on my own. Let me know if you get something similar. That's moles of iron. So how will I get moles of electrons? Moles of electrons. The information they gave me was time and amperes. So what does time and amperes give me? Coulombs. So we're going to get coulombs, right? So coulombs equals amperes times seconds. Amperes is 0.8 hours, not minutes. What does that mean I have to multiply by? You said it's 2 hours. So how do I get that to seconds? Ramon?
Multiply by 3600.
Or multiply by 60 to get to minutes, and then multiply by another 60 to get to seconds. So 2 times 60 times 60, right? Because 2 hours times 1 hour, 60 minutes, if you want the proof, times 1 minute, 60 seconds. I figure you all can grab that information, but that's what that is. 2 times 60 times 60. So then what would that C be then? I get 5,760. C is 5,760. Is that moles of electrons? No. So what do we do now? Is there a relationship between coulombs and moles of electrons? That's called the Faraday, right? 96,500. So we divide 96,500 coulombs is 1 mole of electron. Divide these two numbers, 5760 by 96,500, I get 0.0597 moles of electrons. All right, so now we know the amount of moles of iron, and we know how many moles of electrons are transferred for that many moles of iron. So what can we do now to figure out the charge? Isa?
Yeah, we divide the moles of electrons per moles of iron to get the relationship
Right.
between electrons and iron.
Right. So 0.0597 moles of electrons divided by 0.01989 moles of iron will tell me the relationship, how many moles of electrons for how many moles of iron. It's always a 1 on the bottom. So when I divide these two numbers, what do I get? 3. So what does the charge have to be? Because that means that this is 3 to 1, right? Which means that this is also 3. So the oxidation number is. So that's a way that gamers can ask the question. It's always going to be twisted in a way to make you think deeper than just what is the formula. And so that's the first part. That's what I thought I might be able to get through last class, but apparently I was way wrong with that. So we've got just a couple more slides to go. I think it's 4. The next 2 are Faraday's equation and a quick question about that. And then the next one is actually very similar to your homework. I figured we'd have the time to go over a question that's very similar to your homework because a lot of people get confused with this homework over the years. So I wanted to address a question that was on a different variant of the Cambridge exam that's very similar to the way it's questioned. So hopefully it'll help you to do your homework better. Just so you're aware, this homework for lesson 2, I'm going to make it due on Friday. So you'll have all week to finish it. I did it in about 15 minutes yesterday, so it took less than half the time with the first one. So I don't think it's that long, but you can make mistakes if you don't know how to make your equations correctly. So you got to know how to make your equations. Yes.
Have you both of the 0 and 7 like that?
This?
Yeah, to write on it. It's gonna be
Divide 0.0597 by 0.01989. 0.0597 divide by 0.01989 in your calculator. What does it give you? Divide these two numbers. What does it give you? Okay, because it should be 3.
Yeah.
And if it gives you 3, it's actually 3 over 1 if we're making a relationship, right? So 3 of whatever's on the top and then 1 of whatever's on the bottom, to clarify. All right, we're almost done. So Faraday's equation. This is actually a.
Pardon the interruption. At this time, extended tech students and 9th grade students who were scheduled for the PSAT, please report to the media center.
Oh, wow.
We are on regular bells today.
Yeah, we started late. I guess they'll have lunch late. No, that's not today. Okay, so this is the second formula we're looking at, but it's gonna be a pretty short formula. They said you need to be able to state and use this formula. So this is the relationship between current and electrons. This is called the Flee formula, and this is how we establish the Faraday. So the Faraday is defined as Avogadro some reason. It's how it is. I don't know why, because I've never seen it as L anywhere else besides the standard. Like in my years as a chemist, I've never seen it as L, but okay. So L is Avogadro's number here, and I'm guessing that's the physics letter for Avogadro's constant. Look, you could look it up if you're not already. Where did they derive L from? Where did that come from? Because that doesn't make any sense to me. The letter L is nowhere in my head. I'm gonna go through with that.
It's Avogadro. Like,
This is Avogadro's number, that's 6.02 times 10 to the 23rd. And then E is the charge of a single electron.
can't spell Avogadro without L.
Miss,
Yeah. What is it?
It's to honor the person that actually found it, named Joseph Loschmidt. So it's the L for Loschmidt.
Loschmidt. Okay, so he found it. Is that the person who found it like through electrolysis? Like he did the experiment and determined that that's what it was? Like,
Wait, so it's not Avogadro?
Avogadro's the one that popularized it.
yes.
Of course.
Just like there was another person also working on the periodic table that wasn't meant to leave.
or
And I don't know their name.
or there's
It's
just
actually over for them. Like whoever speaks louder.
Charge of a single electron, which is on your paper as well. The charge of a single electron is negative 1.60 times 10 to the negative 19. And electrons are negative, which is why it's a negative in the front. So do me a favor and do 6.02 times 10 to the 23rd and multiply that by 1.60 times 10 to the negative 19. What number does that give you? If you take those two constants and multiply them by each other.
Wow, 96,320.
6'7"?
No!
Nobody said 7.
I get 96,320, right?
What? Where did I get 6'7"?
What if we added an additional significant figure to Avogadro's constant and did it the way that they have it in the back? What if it was 6.022?
Wait, did you get 6 in your calculator?
Oh, I heard 6'7".
Yeah, honestly, I heard 6'7".
You good, Ben Tomo?
I heard 6'7". I was just going crazy.
Wait,
I get 96,352, right? So it turns out as you use more and more and more significant figures, the closer you're going to get to what number?
Oh, that one, Faraday thing.
The Faraday, right? But this is very close to the Faraday. So if you take the charge of an electron and you multiply by the amount of atoms in a mole, you get the charge on a mole of electrons. That's what this formula is. So for the standard, you have to be able to state this and be able to use it in questions. What do you mean how to use it in questions? Well, let's take a look at the next slide so we can see how we could possibly apply this to a question. Ready?
Wait, this guy's a thing.
An accurate value of the Faraday constant is 96,045. An accurate value for the charge in an electron is 1.6022 times 10 to the negative 19. Use these values to calculate the value of the Avogadro constant to 5 significant figures. So this would be using the Flee formulas. F equals L times E. So what do we plug in for F here? Plug in 9645. Here you're solving for L. So you're solving for Avogadro's constant. And then what about E? Why like L is never barely used, so it's used if somebody wants to honor the person? Is that what you're saying?
Yeah, because his constant is completely different constant, but his is the foundation for the other.
Or where it came from? Because it's not used popularly. I've never seen it besides here that I can remember.
Hey, you get 6.022.
So divide by 1.6022 times 10 to the negative 19. Divide by 1.6022 times 10 to the negative 19. And how many significant figures did they say they wanted? Okay. They said 5, right?
I said 5. You've lost it. Well, 6.0.
I get 6.0220.
Bro, why is it
Times
no
10
six
to the
seven?
23rd. Now,
It should be 6.0007.
Perfect.
67.
all right, so we're about done, but before we go, your last question on the homework, I know that students tend to struggle with. So I found an exam that had a different variant of this type of question, but the type of question is the same. So we could address it. Now that we've addressed these two formulas, I think you're ready to solve some Cambridge questions. So on the next two slides, you'll see that there are 1, 2, 3, 4, 5 marks. 5 marks here. And I could have given this as a bell work next class, but I decided against it because I wanted you all to get your bell work right. So
We need a redemption.
saying, I'm just saying that I know how things tend to go. And I saw what happened with that 5th question in today's bell work, so we need to review this. But this will definitely help you with your homework. So let's take a look at the question from Cambridge. This is a paper 4 question. 5 marks out of how many? How many do you have on a paper 4? 100 marks. So
Crazy.
this would be 5% of the test. Pure water is a very poor conductor of electricity. However, if we took HCl gas and dissolved it in water, we would form ions. Well, yeah, it'd be hydrochloric acid. And a current would flow during electrolysis. So they're telling us that we could electrolyze this. The overall change after electrolysis, if I electrolyze HCl, which is hydrochloric acid, is that I would get hydrogen gas and I would get chlorine gas.
You stole my pencil. Yes, you did. I was
So when a current of 3.1 amps is passed through a solution for we don't know how many minutes, 351 centimeters cubed of chlorine gas are produced at the anode, measured under room conditions. Can you calculate the number of chlorine molecules that have been produced for 2 marks? What would we do? What would we start with here? Go ahead, Lisa.
We first have to convert the volume to moles using
So we use the information we have for chlorine. This is the information that we directly have for chlorine. And what we have right now is we have the volume of chlorine. Well, what is the volume of? Cl2 gas, right? Because that's how we would measure a volume. It's the gas. It's filling an amount of space. Chlorine gas. Yikes. But so we would start with that. I would change my 351 centimeters cubed to decimeters cubed immediately. That's how I did it in my work. And I would say, okay, so this is 0.351 dm cubed Cl2. That's what I have. And how would I get that to a number of molecules? What would I do? Right now? Is that the first thing I should do? What's the first thing I should do? I should change dm cubed to moles. And then once I've got it in moles, then I'm going to change moles to molecules. So I've got a 2-step path here. So then how do I change dm cubed to mole? What do I use? Look at all the numbers we're using on this sheet today. Like, it's on here, right? It says room conditions.
Oh, I didn't see.
So you have to look for which situation you have. So it says room conditions. So we're going to use which number? 24. Okay, that got me to moles. Now what? How do I get to molecules? Moles to molecules. 6.02 times 10 to the 23rd molecules. And so that's going to give me here 8.80 times 10 to the 21. Molecules. 2 marks. You can do that. Yes.
Between atoms and molecules.
There sure are. I know you're so excited to work with that. It's 1 molecule Cl2 equal 2 atoms Cl2. So if 2 atoms Cl. So if you were asked for atoms, you would have to take that number and multiply by 2. Okay, that's not the question. So let's keep going. Calculate the total number of electrons transferred to make this amount of chlorine. How could we figure that out? So, do we have a relationship between chlorine and electrons right now? Well, how can we get that? How can we need to make an equation? So if we need the amount of electrons, we've got the amount of chlorine, we need to make an equation, don't we? Oh, so wouldn't that be the 2Cl minus goes to Cl2? That because we're doing chlorine, right? What am I missing? The most important part. You have to fill in the amount of electrons. How many and on which side? 2E minus on the product side, right?
Two.
Why not the product?
Uh,
Isn't it got to be the charge balance? It's got to be on the product side?
Yeah,
Yes? All right, so I've got a relationship. Now what? What can we do now? What should we do now? 8.80 times 10 to the 21 molecules. Can't we just say that one Cl2 molecule has how many electrons? One Cl2 molecule has how many electrons? 2, right? It's double the amount of electrons than Cl2. So the net result is we're just multiplying our answer from the first one by 2. And so this should give us 1.76. Check my rounding, but I did 1.76 times 10 to the 22nd.
7.6.
Yeah. It is what it is. I pray for your Cambridge examiners in May and June.
I just purposely rounded to like
Can you
6.7.
imagine?
I underlined it.
Every answer you don't know
Oh yeah,
I
just put 6.7.
in memory.
Just put 6.7.
All right, ready to continue?
Nothing back.
Are we good with this? Did you understand how I got this? Does this relationship make sense? Multiply by 2. All right, so we continue. Calculate the coulombs of this amount of electrons. Could we figure that out? How would we find the coulombs for that amount of electrons? So we're going to have to start with this. We have 1.76 times 10 to the 22nd electrons. How can we find the coulombs? Well, first one I got to get to moles because I need to go from single electrons to moles of electrons. This is where everybody got stuff in the past, so that's why I'm going over it with you. And then I would go from moles of electrons to coulombs. So what do I mean go from electrons to moles of electrons? Electrons are particles. They can be gathered just like atoms or molecules, right? So we can say, that's the phone. Hello, this is Miss Leeds. Yeah. Yeah, I can talk real quick. Yes. Yes. Okay, because there was something, I'll fix it because it was something from before that I put in later. It was from like 2 weeks ago, but it was the first assignment that I had. I held it for the next quarter. So do you want me to fix that real quick? I understand. So that's a start. Yeah, that's a due date. I'll fix it right now for you. No problem. Okay, let me make something real quick. Her blood cell.
I said 34.
Let me just double check. Okay. So, do we understand this thing? That it's going to be 6.02 times 10 to the 23rd electrons in 1 mole. Does that make sense? Yes.
It's like a mole of atoms is a certain number of electrons.
Any mole of anything is 6.02 times 10 to the 23rd. So after
Oh.
single thing, I have to gather 6.02 times 10 to the 23rd of them to classify them.
Ah.
So because I had single electrons here, I have to turn them into moles. This is the part where everybody in the past has gotten really confused. That's why I want to make sure to go over this. So when you get it in your homework, you're going to get a very similar question to this, different numbers, but the same idea. So I wanted to address it with you here because I figured we'd have the time and we do. All right, so now what?
Then cool.
Coulombs. So 1 mole of electrons is how many coulombs? 96,500. That's the number that I use. It's the number that's there. And so I get my coulombs is 2820. Do you agree? To 3 significant figures, 2820. They accepted 2822, I think, or they gave like a range of answers they accepted, but I rounded mine to 3 significant figures. And then the last part, can we calculate that time now? How do we calculate the time? We've got the coulombs. Do we have the amperes? We have to have the amperes. Oh, they're all the way back in the reading. We have to read it. It's there. And so C equals A times S. So let's say I couldn't figure out the coulombs, or I got something that insanely looks totally wrong. Like I forgot to use 6.02 times 10 to the 23rd, and I got like an insane amount of coulombs. Could I get error carried forward if I just plugged that insane amount of coulombs in here and knew to use this formula? Yes. Error carried forward applies to all these questions. So make sure, even if your answer doesn't look like it makes sense, continue on with the process. You probably did make a mistake, but don't lose the error carried. Like, don't leave it blank. At least attempt it, because you could get the error carried forward out of it. So this is 2820 equals 3.1. What?
That's 7.
Huh?
If you divide 28, so you divide by 3.10, get 909.677.
Oh no. I stopped mine intentionally, I guess, at 909.
No!
909. Because I only have it written as 909 here.
67.
Too bad, so sad. Is it 910 then?
Yeah.
910? Yeah. Okay, 910. But is that the answer? If I wrote that, would I be right? I'd be cooked. Because they asked me for what?
Minutes.
Minutes for 1 mark. So if I don't forget to change that second to minute, by knowing 60 seconds is in a minute, right? So divide 910 by 60. And the answer is 15 points. What did you get? 16.2 minutes. And that's it. All right, so we have finally finished electrolysis. Woo! 2 classes for that 1 lesson. So you can go ahead and get started on the homework. For those of you that didn't finish the titration questions, maybe you should go back and finish those. You've got about 20 minutes left in class. Yay! So next class, remember, we've got a lab that you need to be well prepared for. So either start working on the next homework or finish up the last one. I put the answer key so you can also revise your homework during this time. Yes. Yeah, you can sketch your own book. Yes, that's it.
We need to make our titration, do the titration.
No. That's what I mentioned in class, so you should do those now. So either work on last class's homework that was due today, revise it, I put up the answer key, or start on electrolysis. You got some time. Yes.
Why do you keep calling him Coulomb? It's Coulomb.
I'm gonna call him cool.
Why? It's lattice.
Coulomb.
It's I don't know. Why do you keep doing that? Lattice, Lattice.
Maybe somebody told me it was Lattice as a teacher and I just stuck with it. Maybe.
You said thermodynamics. What
Thermodynamics.
even is that? But when you said
I was
thermo.
probably tired. Thermodynamics.
Stop doing that.
Go ahead. After she comes back. Potato, potato.
Am I? Or are you saying everything right? I'm just like.
I'm driving Daniel crazy.
God, I will.